Hey there, this is the video for Chapter 5, Section 1. We're going to be working a lot with the standard normal distribution today, so make sure you have handy the tables I gave you in class, or look them up ahead of time in your e-text. They're located in Appendix B and is table number 4. There are a few pages to it. Again, that's Appendix B, Table 4. Pause the video and take a moment to find those if you need to. You'll need to have them handy for the examples. Also, you will be using your calculator quite a bit, so wherever you're putting your calculator notes, keep those close by as well. If you have a ruler or something else you can use as a straight edge, that may help keep track when you're using the tables also, either on or off the screen. These numbers can tend to run together. I'm going to try to give you a good feeling for the big picture of what these graphs mean, but please ask questions in class if you're not getting it. This stuff can be very confusing, and it's okay if you're not quite there. Trust me, you're probably not the only one. Okay, let's dive in. Welcome to the lecture video for Chapter 5, Section 1. This section focuses on learning how to read a normal distribution. Our objectives for today will be to identify a normal probability distribution and to be able to find areas under the standard normal curve. As a quick review, in Chapter 4, we introduced what are called random variables, which represent a numerical value associated with each outcome of a probability distribution. And we had two types, discrete and continuous. The discrete types were integer values, like 1, 2, 3, etc. Continuous variables were any value in an interval. When we talked about graphing these sorts of distributions, we said that discrete graphs would be bar graphs, like this on the left, because they represent non-negative integers. We looked at three specific types of discrete random variable distributions: binomial, geometric, and Poisson distributions. They could all be graphed with a bar graph, and we could find the exact probability whenever x was equal to a particular number, and the values of x could take on as the random variable were non-negative integers. Now we're going to be talking about continuous random variables. It can now be any number between any given 2 points on the number line. Because it can be anywhere within a range, it means I have to graph it as a continuous line in order to include all the possible values in between those two numbers. So because it's a curve on an xy plane, we're talking about a function. So that's where we're going with Chapter 5. We're going to begin by talking about maybe the most important probability distribution in statistics. And the graph of this distribution is called the normal curve. We've already seen this in previous sections. We talked about symmetric bell-shaped curves, and that's exactly what this is, the normal curve. Here are some properties of a normal distribution or a normal curve. The mean, median, and mode are equal and all align with this central symmetric line. The normal curve is bell-shaped and is symmetric about the mean. The total area under the normal curve is equal to 1. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. Also, as we've talked about before, as you move away from the mean in the center of a normal curve, you systematically move in lengths of standard deviations away from the mean. The mean is represented by the lowercase mu symbol, and the standard deviation is represented by the lowercase sigma symbol. As you move to the left, you can say that one standard deviation less than the mean is at the mu minus 1 sigma point on the graph. If you move to the right, the same distance from the mean, you are at the mu plus 1 sigma spot on the graph. These 2 points are very important and are called inflection points. Notice how the graph changes at these points. From the mean down to these points, the graph has a downward curve. But when you reach the inflection points, or the 1 sigma point, where the first standard deviation falls away from the mean, the graph changes from a downward curve to an upward curve. This is an important distinction to be aware of. An interesting fact about a normal distribution is that it can have any mean and any positive standard deviation. The mean gives the location of the line of symmetry. The standard deviation describes the spread of the data. Look at the graphs below and notice the location of the mean and how the size of the standard deviation changes the look of the graph. See how the larger standard deviation makes the first graph wider than the other two with smaller standard deviations? Look at the two graphs below and see if you can determine which has the greatest mean. Remember, the mean is the anchoring point or the line of symmetry for the graph. Pause the video for a moment to decide this. It looks like the line of symmetry for graph A is sitting at about 15, and the line for graph B is at about 12. So graph A has the greater mean for this picture. Let's try another one. Which curve has the greater standard deviation? Now remember, this is related to the spread of the data points. Pause the video and decide this. Curve B is definitely more spread out than curve A, so curve B has the greater standard deviation. Its data points are more spread out. Here's a different kind of example. The scaled test scores for New York State Grade 6 Common Core Mathematics test are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? Estimate the standard deviation of this normal distribution. Okay, so they're wanting us to find the mean and the approximate standard deviation. What do we know about locating either of these numbers? Well, the mean is the anchoring point, the line of symmetry or center. So it looks like the line of symmetry for this graph is at about 600. That's the point at the very top of the curve and the very center. The next part is a bit trickier. Remember how we said the first points of standard deviations were also where the inflection points in the curve changes from curving downward to curving upward? Well, it's a little tough to tell where that happens here because there's a long section where it's sort of straight. But it would be reasonable to assume that the point where it actually changes is in the middle of that straight area. So I would say that the inflection point is in the very middle of that straight area. That's where it stops curving down and starts curving upward. So I would say the inflection point is probably right in this area in the middle of that straight area. And that would hit at about 620. So I would say inflection point on the right is at about 620. The inflection point on the left is at about 580. So that is about 20 from the mean that we decided, 600. So that would mean that the standard deviation is about 20. So our mean, we're saying, is about 600, and the standard deviation is about 20. Let's see what they thought. It looks like we were right. Yes, they interpreted this the same way. Because the normal curve is symmetric about the mean, you can estimate that mu is about 600. And because the inflection points are one standard deviation away from the mean, we could estimate that sigma is 20. The scaled test scores for the New York State Grade 6 Common Core Mathematics test are normally distributed with a mean of about 600 and a standard deviation of about 20. Okay, now we're going to focus on a very specific normal distribution. First, let's look at some properties. A normal distribution is a continuous probability distribution that can have any mean and any standard deviation. Okay? A normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution. This is a very specific normal distribution and is used a lot in statistics. Here's what that graph looks like. You could substitute mu plus 1 sigma for positive 1, mu minus 1 sigma for negative 1, and so on, and mu for the 0. When you're looking at a non-standard normal distribution, any x value can be transformed into a z-score by using this formula. Z equals the x value minus the mean, mu, divided by the standard deviation. This is an important formula, so make sure you get this down and make sure you have the subtraction in the right order. You're always subtracting the mean from the x value. Here you can see that idea translated into graphical form. If every data value of a normally distributed random variable x is transformed into a z-score, the result will be the standard normal distribution with a mean of 0 and a standard deviation of 1. This is not some kind of mathematical magic. It's a way of standardizing something so that there is a way to compare unlike things. Statisticians use this to compare statistics that are measured differently so that instead of looking at apples and oranges, everybody's now looking at grapes. but in a way that makes sense to everyone. It's like the universal translator of statistics. So when everyone has statistics that are measured with different means and different standard deviations, they can translate them into standard normal distributions, then everyone is looking at them with the same scale. Okay, let's look at some examples of how to use all this information. Okay, here is where those tables I gave you come into play, or where you need to have pulled them up from your e-text. That was in Appendix B, Table 4. Pause the video to find these things if you didn't at the beginning. Appendix B, Table 4, or pull up the pages that I gave you in class. We'll start off by just finding the area under the curve that corresponds to a z-score. This means we're given a z-score, and we're finding the z-score in the table, which represents the area of all the space to the left of that spot under the standard normal curve. We'll get to what happens to the right and elsewhere later. For now, just know that when you're looking at a z-score in the table, the number you see there represents the area to the left of that z-score under the curve. So let's look up the cumulative area that corresponds to a z-score of 1.15. Here's how to read this table. You first look down the first column that has a z at the top. Look straight down to find the first few digits of the score. These do not represent the whole number, just the beginning of it. For this example, we're looking for positive, that's important, 1.1. So there it is. We note this row to follow along straight across. Here's where that ruler would come in handy if you need it. Now we need to look along the top for the last part of our number, the hundredths place, or 0.05. See it over here to the right. Now we follow that down until it meets the row and it intersects. So then we have our area. The area to the left of z equals 1.15 is 0.8749. All right, let's try another one. Find the cumulative area that corresponds to a score of negative 0.24. Okay, it's very important to note that this one is a negative number. When we're looking at the table, we want to make sure we're looking at the negative beginning z-scores. So we'll look for negative 0.2. After that, we look for the hundredths place across the top and find 0.04. We follow that down to the intersection and find 0.4052, and that is the area to the left. It's at this point that we should talk about a few key ideas with regards to area and z-scores. Look at these graphs. The first one represents a z-score that is negative and very, very small. The smallest z-score on the chart is negative 3.49. When you get closer and closer to a z-score of negative 3.49, the cumulative area under the curve gets closer and closer to zero. And this kind of makes sense, right? A tiny bit of space is being accounted for, so it's not covering much area. So the lower the z-score, the closer to zero the area is. Now look at the second graph. This one represents a z-score of 0, which is in the middle where the mean is. Exactly half of the curve is accounted for. And if you'll remember, the entire curve has an area of 1. So if exactly half of the curve is accounted for, guess what? Half the area is too. So the cumulative area when the z-score is 0 is 0.5, or a half. Okay, what about this last one? Well, the highest possible z-score is positive 3.49. So the closer the z-score gets to that, the closer the area gets to 1, since the area under the entire curve is 1. Does that make sense? If you need to pause the video to think about this concept for a minute or jot down this idea, go ahead. It's a concept that'll help you later, hopefully. Okay, let's consider 3 different cases you may be presented with when finding the area under a standard normal curve. The first is finding the area to the left of a z-score. You actually already know how to do that one. You just find the z-score in the table. The area listed is the area to the left of that z-score value. So let's do one of that kind. Sketch the standard normal curve and shade the appropriate area under the curve. Find the area by following the directions for each case shown. To find the area to the left of z, find the area that corresponds to z in the standard normal table. See? Exactly as we did before. So we use the table to find the area for the z-score. The z-score is 1.23, so we look it up on the table. The area to the left of z equals 1.23 is 0.8907. That's all we have to do for that kind. Let's look at another situation you could face when you're looking for area under a standard normal curve. To find the area to the right of a z-score, you're going to find the area on the table that corresponds to the z-score, but then you're going to subtract that number from 1. Look at it this way. You use the table to find the area for the z-score 1.23. We know the area we find on the table, which in this case is 0.8907. That's the area to the left of the z-score. So that's actually giving us the tan area instead of the blue. Since we know the area under the entire curve is 1, that tells us we can subtract the area we know of, the 0.8907, the tan area, from 1 to get the remaining area of the blue section. So when we subtract 1 minus 0.8907, that gives us 0.1093. That is the area of the blue section, 0.1093. So that's how you find the area to the right of a z-score. Okay, let's look at the last situation you could face when finding area under the standard normal curve. To find the area between two z-scores, you'll need to find the area of each of the z-scores, then subtract the smaller area from the larger one. Let's go through it step by step. First, you use the table to find the area for the z-scores. In this case, find them for 1.23 and negative 0.75. Using the table, we come up with the area to the left of z equals 1.23 is 0.8907. That includes both the blue section and the tan section because they are both to the left of 1.23. Then we find the area to the left of z equals negative 0.75, which is 0.2267. That's just the tan section. Now, to get the area of just the blue section, we need to subtract the area of the tan section, or the area we got for z equals negative 0.75, from the total area left of z equals 1.23. So, we do 0.8907 minus 0.2266 equals 0.6641. That gives us the area of the blue section, 0.6641. Okay, let's try a few more, but this time I won't tell you everything that you need to do. I'll help walk you through the table. Find the area under the standard normal curve to the left of z equals negative 0.99. They give you a picture of about where that falls on the graph, and here's what the table looks like for that section. Pause the video and find the area. So you'll look at the z column first, find the beginning part of your z-score. So in this case, that would be negative 0.9. Then you would look across the top for the hundredths place, or 0.09, and look for the intersection, and there is your area, 0.1611. That is the area of the blue section. Next one, find the area under the standard normal curve to the right of z equals 1.06. They give you a picture, and here's the table. Pause the video and find the area. Okay, so you look for the z column first, find the beginning of the number, 1.0, then you find the end of your number, 0.06, then you look for the intersection, 0.8554, then you got to think about this, they want the area to the right of z equals 1.06. So what do we have to do next? We have to subtract that number from 1. So 1 minus 0.8554 equals 0.1446. That is your area of the blue section. All right, one more. I bet you know what you're going to need to do here. Find the area under the standard normal curve between z equals negative 1.5 and z equals 1.25. Okay, here's our first table. So we look under the z for the first part, is negative 1.5. Then we skip several columns over to the column that represents 0.00 because it's just negative 1.5. There are no other numbers, so the hundredths place has to have a 0 in it. Then we look where those intersect and get 0.0668. Now this is just the area of the tan section. Next we need to look at the other z-score. I'll give you just a minute to find that score on your own. Okay, so we look under the z for the first part of our score, 1.2. Then we find the second part, then our intersection. Now I'll give you a moment to figure out what you're supposed to do with those two numbers. If you subtracted the smaller one from the larger one, you did the right thing. And you should have gotten 0.8276 as your area. How'd you do? So would you be happy or concerned to learn that there is a calculator shortcut for this process? You still need to understand whether you're looking for the area to the left, right, or between two z-scores, but the process is simple. Okay, ready or not, we're going to learn it. Make sure you get the process down in your notes. Okay, this one is called the cumulative density function, or normal CDF. Here's how you enter it. Very similar to some of the others we've done lately, except this one's much closer to the top of the list. To use the cumulative density function, press the second key, then the vars or variable key to pick dis or distributions menu above it. Select to normal CDF, not PDF like we've done before. You want CDF this time. Then press enter. Now, depending on your calculator, and you should know by now whether you're going to be pressing enter between the numbers or typing commas between your variables and closing parentheses. And now you're going to enter your variables. For the lower bound, this is the left side of your graph that you're computing. There are three choices of how to fill this part out. One of them, if you're doing a left of z-score problem, you want to put a very large negative number in scientific notation like it's listed here. The way they've done it, they have done it in scientific notation. So they've done -1, then the second key, then the comma button, which has the inner exponent or EE option above it, then 99, which basically tells the calculator -infinity or a very, very big negative number. Your second option for lower bound is if you're doing a right of z-score problem, and you would want to put the z-score here in your lower bound. Your third option, if you're doing a problem where the desired area is between two z-scores, you put your lower bound as the leftmost z-score here. So those are your three situations. Depending on what type of problem you're doing will determine which option you're going to put in lower bound. And then if you look to the right, there's your upper bound. That's your next choice that you need to enter. And this also has three options of what you're going to enter. And it depends on what type of problem you're doing again. The first one, if you're doing a left of z-score problem, you're going to put the z-score in your upper bound, because that would make sense, right? Your upper bound is going to be your z-score because that's what's on the right side of your graph. Your second option, if you're doing a right of z-score problem, you want to put a very large positive number in scientific notation, just like what we had listed to the left, just without the negative symbol. Your third option, if you're doing a problem where the area is between two z-scores, you want to put in your upper bound the rightmost z-score. Then your next choice is your mu or mean, and this should always be 0 because we're doing a standard normal distribution. And sigma or standard deviation should always be 1. Then press enter and then press enter again to calculate. If you need to pause the video to get these instructions down, please do so. Okay, I need to make an important note here. Because your calculator allows you to put in left and upper bounds, you don't have to mess with the steps that require you to subtract from one or subtract one area from another when you're using the calculator. Your calculator does all that calculating for you. See, it doesn't have the restrictions that using the table does, so you don't have to do those extra steps. It's doing those steps, but in the background, so you don't have to. So, important tip to remember. If you're using the table, you do need to subtract from 1 if you're doing an area to the right of a z-score problem, and subtract one z-score from the other if you're doing a between z-scores problem. But you don't have to do either if you're using your calculator. You just have to know which one you're doing and put the correct left and upper bounds. Got it? Okay, let's move on. Use technology to find the area under the standard normal curve to the left of z equals negative 0.83. Pause the video and do this now. Did you get it? You should have gotten about 0.2033. If that's not what you got, rewind the video and make sure you're entering correctly for this type of problem. You should have had a very large negative number for your left bound and negative 0.83 for your upper bound, and then 0 for your mean and 1 for your standard deviation. All right, let's try another. Find the area under the standard normal curve to the right of z equals 1.43. Pause the video and do this now. Okay, how'd we do? Did you get 0.0764? Did you remember to put the z-score as your lower bound and a large number as your upper bound? Try it again if you missed it. Okay, last one. Find the area under the standard normal curve between z equals negative 1.35 and z equals 1.4. Pause the video and find this area. Did you find the area to be 0.8307? If so, great work. If not, go back and figure out what you might be missing. Or if you can't figure it out, put a star next to it on your notes and ask in class. Okay, I know this was a lot, but you're doing great. Thanks for all your hard work. Talk to you in the next video.